In the last few videos, we've been talking about cool consequences of knowing that a quadrilateral is a parallelogram. Those parallel sides really have a lot of cool things that are forced out because of that condition. And because of that, it would be neat to be able to know that a figure is a parallelogram without having to know that there are parallel sides. The conditions probably work in both ways. And so there are lots and lots of ways to prove that something is a parallelogram without not necessarily knowing that the two pairs of opposite sides are parallel to each other. And that is the second part of the parallelogram line in the quadrilateral reference sheet. So let's take a quick look at what I've got written there. And so you can get a bit of a preview. So down here, underneath all of the facts about parallelograms, we have other ways of proving a quadrilateral is a parallelogram. What we're going to show in this video is that if you've got one pair of sides that are both congruent and parallel, that's enough to be sure that the figure you have is a parallelogram. We're going to prove that in this video. In homework, we're going to see that knowing that two pairs of opposite sides are congruent, instead of knowing that both pairs are parallel, you would know that both pairs are congruent. You can also know if the diagonals bisect each other, then that quadrilateral has to be a parallelogram. You'll do those two, look at them in homework. And knowing that consecutive angles are supplementary, that's kind of the same argument that we gave in the last video about looking at the parallel sides, and the consecutive angles are same side interior angles. So they have to, if they're supplementary, then the lines that form them have to be parallel. So we're not going to discuss that, but that is another criterion for knowing that a quadrilateral is a parallelogram. Well, let's prove the first one, that if we have this quadrilateral and we know that the top and bottom sides are both congruent and parallel, that's enough to know that we've got a parallelogram. So what I want to do right now is I want to do this proof in the waterfall style, the flowchart style. So I'm going to start off with my givens at the top. I'm going to start out with AB is congruent to CD. That's given. And now I'll get a box. And we know that AB is parallel to CD. That is also given. And another tip that I have talked about before, but let's take a look at it right now, is that if it's hard to know where to go in a proof, you can put the to proofs statement at the bottom of the proof. All right, so down here at the bottom of the proof, we're going to say ABCD is a parallelogram. I don't know what goes in the middle, but I do know that when I'm done, this is what the last line has to be. The last line has to be the thing that we're going to prove. And I don't know the reason for it yet, so I'm leaving that blank. So I got some ideas of how to get started now, because now, once again, like in the previous proofs, I've got a vocabulary term here. So I know that I'm going to be able to prove this by saying that ABCD meets the conditions of a parallelogram. Once again, if I got out my reference sheet, I would know that means the opposite sides are parallel. Well, that's cool. I already know that this side is parallel, so I'll just drop a great big arrow from here down to here. But I also need to prove that the other pair are also congruent. So I also need to show that the left and right sides are also parallel. So I need to prove over here that AD is parallel to BC. And I don't know what the reason for that's going to be, but I know that if I prove that and I've already got this statement, then this is going to be true, because that's the definition of a parallelogram. So working backwards feels kind of weird. You're writing in statements before you've got a reason, and then you figure out what the reason is, but then it gets you to write a new statement with no reason. All right, so that's kind of interesting. What would I need to do in order to prove that AD is parallel to BC? Well, again, if we went back to our proof reasons reference sheet, and I'm not going to pull it out every time like I did the last time, but you can prove that two lines are parallel if you can show that you've got alternate interior angles that are congruent to each other. So once again, I'm going to draw my pink sides here. So those are the sides that I need to show are parallel. And so I can just, once again, write in an auxiliary line, which is one of my diagonals, and now I've got that mark of Zorro going for me. So in order to prove that these two lines are parallel, I would need to show that this angle right here and this angle right here are congruent to each other. All right, so the one angle is angle ADB. ADB is congruent to angle DBC. And once again, I don't know the reason that this is true, but if I were able to show this is true, then I can conclude that those pink sides have to be congruent. I'm sorry, that they have to be parallel because those are alternate interior angles. Okay, the alternate interior angles of this mark of Zorro are congruent, so therefore the pink lines have to be parallel to each other. All right, so what that's doing, working up from the bottom, it's giving me a much clearer idea of what I need to prove. I need to prove that this dotted angle there is congruent to that dot right there. Okay, and that kind of looks like the way I'm going to prove that is to show that this triangle is congruent to this triangle. Okay, so if I were able to do that, then those two dotted angles would be corresponding sides of those two triangles. All right, so once again, this way we're totally working up from the bottom and instead of working from the top down. So if we prove that triangle ADB is congruent to triangle, remember, ADB. So we're starting in the far corner, going up the pink side, and then going across the diagonal. So in the other triangle, it's going to be CBD. CBD. So if I were able to prove this, then I'm going to know that this is true. I just proved that two triangles are congruent. I've got congruent triangles. So I'm going to show that two angles, these two dotted angles, which are corresponding parts of those two congruent triangles, they have to be congruent because that's what CPCTC says. All right, so now instead of having this statement way down here about a parallelogram, now all I need to do is prove that these two triangles are congruent to each other. And what do I have to do that? Well, I've got this side right here is congruent to this side. That was given. And what other facts do we know? We also know that the two sides are parallel. The top and bottom sides are parallel to each other. And when we've got parallel sides in a parallelogram, once again, we want to look for the mark of Zorro. How are we going to draw a mark of Zorro in this? Right down the diagonal there. So we know that this angle is congruent to this angle. So angle CDB is congruent to angle ABD. Once again, because we've got alternate interior angles. Notice how we're using alternate interior angles in both ways in this proof. We've got parallel sides, so therefore the alternate interior angles are congruent. Down here, we did the opposite. We said we've got some congruent alternate interior angles, therefore the lines that form them must be parallel. Both of those are legitimate ways to use that theorem. So we've got two parts. We've got a side and angle of these two triangles. What can I use for my third side? I'm fresh out of givens. I've squeezed everything I can out of the givens of this proof. And that usually means that we want to see if we can use the reflexive property or if we can use the vertical angle theorem to pull facts kind of out of nowhere. And in this case, we're going to use the reflexive property because that diagonal is a common side in both triangles. So off here to the side, I'm going to write BD is congruent to BD because of the reflexive property. One fun thing about these waterfall proofs is that they start to be a little bit, a little bit tangled up. You can always, if you wanted to, make a fresh sheet of paper and kind of make it a pretty diagram by the time you're done. And some people used to make waterfall proofs and then turn it into a 2-column proof once they kind of figured out how everything is laid out. So now the only thing we have left to do is to tie all of our facts together and justify this triangle congruence statement. So we need 3 congruent sides and angles pointing into this. There's 1, there's 2, and there's 3. And we need to fill in the reason here. So once again, what we can do is we can cover up one of the triangles if we want to, and then see, either with our triangle congruence sheet or without our triangle congruence sheet, see if we can figure out what our reason is. All right, so here are our 5 reasons, and here's what the one triangle looks like. So we've got 2 sides, and we've got the angle between them. 2 sides and the included angle. So it looks just like this triangle right here. And the word itself, SAS, is 2 sides and the angle between them. 2 S's and the A between them. So all we need to do is fill in this as SAS, and we have a complete proof. So it's one nice thing about the waterfall proof. We can see that we're using all of the givens. We can see that every box we wrote is flowing down to the consequence that we needed to prove at the bottom. The givens are at the top, the to prove is at the bottom. Everything is being used. So that was kind of a neat proof. So what we just did is we showed that since the top and bottom of this parallelogram, we were given both that it was parallel and that they're congruent. And that was enough information to say that that was also a parallelogram. So now, not only can we work with knowing that 2 pairs of opposite sides are parallel, but we can also work from knowing that 1 pair of sides are both congruent and parallel. In the homework, we'll see a third reason, which is if we can show 2 pairs of congruent sides that are opposite of each other. If the 2 congruent sides weren't opposite each other, we would have a kite instead of a parallelogram, which is not a parallelogram. Okay, so that gives you an idea of how we're using proofs, both to say, hey, this is a parallelogram, what can we do with it? And to say, what do we need to have happen in order to know that something is a parallelogram? So working in both of those directions with proofs is giving us a lot of power to both recognize and take advantage of parallelograms.